So let us start with what is maxima and minima. Maxima means the maximum value, okay, and minima means the minimum value, okay. Maxima means the maximum value and minima means the minimum value. So let us start with the formal definition. Let f is a function defined on an interval I. Then f is said to have a maximum value in I if there exists a point C in I, okay, there exists a point C in I such that f of C means the value of the function at C is greater than f of x, okay, means f of x means all other values of that function inside that interval, okay. I is an interval in which a point C is also lying, right? So we will say that f is having maximum value in I if the value at point C, say, is greater than all other values of the function in that interval, right? For all x belonging to I. And this number fc we take, it is called as the maximum value of the function in I. And this C is called the point of maximum value. It is called as the point of maximum value. Okay, it is called as the point of maximum value. Similarly, f is said to have a minimum value on I if there exists a point C in I such that f of C is your less than f of x, all other values. C के ऊपर जो value है, that is less than all other values of that function inside the interval. Okay, and in this case, what will this fc called? It will be called as the minimum value of f in I. Okay, and this point C is called your point of minimum value, okay, point of minimum value. Similarly, f is said to have, what is the meaning of extreme value? Extreme means either it is maximum or it is minimum. So extreme value in I, if there exists a point C in I such that f of C is your either it should be maximum value or it should be your minimum value, okay, or it should be minimum value. Okay, so function will be having an extreme value in I if there exists a point C in I such that fc is either maximum value or minimum value. Now, in this case, this fc is called as the extreme value. Extreme means either maximum or minimum. And this C will be here called as the point, is called as the extreme point. It is called as the extreme point. Now, let us see these three figures, how they are depicting. This is a curve in which you see fc, as we have already discussed it in Rowe's theorem, means a point is lying at which this your fc is this, okay. You can find that it is having the maximum value here. This point is the maximum value, okay. So why it is maximum? Because at all other points adjoining to this side or to this side, this function at this point is having its maximum value. Similarly, here at this point, this function is having, means say at this point, this function is having the, this C is the point at which the function is having the lowest value, except other where it is having the greater values as compared to this. So it will be called as the minimum value, and this is called as the point of minimum. And see, this is a curve, like it is having both its maximum and minimum value. So your maximum, this is the minimum value and this is the maximum value, okay. So the curve is increasing one. I will say it is a monotonic function, okay. It is only increasing, right? So such function will always have both minimum and both maximum value. Now let us see example number 26. Find the maximum and minimum values of the function f given by fx equal to x square, x belongs to R. Now first of all, when we will plot the graph, it is very clear that you know that the graph of x square, it's a quadratic polynomial, so graph is a parabolic one. Now from this graph, what you will see that if we will find the critical point, you will find your x as 0, okay. Here this fx is 0 if x is 0, okay. Also your fx is always positive for all. It is always positive, means it is just lying in this first quadrant and the second one, means not below this, okay. It is not towards this negative axis. So we say that for all real numbers this function is greater than equal to 0. Therefore, minimum value of this function is 0. And the point of minima is also your x equal to 0. Right? And also it is observed that from the graph it has no maximum value because it is extending indefinitely in this direction. Also, as we keep on plotting the values, you will find that the no maximum value will be there. So we will say that it has no point of maximum value in R. Okay. And what happens if we will restrict the domain of this function to minus to 1 only, then it will have its maximum value, which is given by putting the value of x as minus 2, that will be 4. Okay. If you restrict the domain, then this question will have both maximum and minimum value. Otherwise, it is just having its minimum value and maximum value is not existing. Okay. Similarly, let us take example number 27. Find maximum and minimum value of the function, and function here is their mod function x belonging to R. So you are also familiar, the mod function graph is this V-shaped graph. Okay. This is for y is equal to x, and this is for y equal to minus x. Okay, this is for y equal to minus x, and this is for y equal to x, and you know they intersect at point 0. Okay. Now here also fx is positive greater than equal to 0 for all x belonging to R, and will be 0 if x is 0. Now the function has a minimum value. Okay, and the point of minimum here also is x equal to 0. Also, the graph clearly shows that it has again no maximum value and it is extending in both the directions. Okay, so no point of maximum value in R. But again, if we restrict the domain to minus to 1 only, then what will happen? As minus 2 mod is 2, so you will have your maximum value also. Now we need to understand what is the monotonic function. Okay, the meaning of monotonic function means either it is taking its maximum value or minimum value. Okay, and this maximum or minimum, it always occurs at the end points of domain of definition of the function. Definitely, if a function is monotonic, means it is increasing only. So definitely at the lowest point it will be having minimum value, and at the highest point it will be having the maximum value. Okay, monotonic. And if it is decreasing only, so at the lowest point means the the lower level point, it will be having the maximum value, and at the maximum point means the greater point, it will be having the lowest value, right? So monotonic function assume maximum and minimum value at the end point, and every continuous function, okay, on a closed interval I has a maximum and minimum value. Always remember, every continuous function, if it is continuous in a closed interval, then definitely it will have maximum and minimum value. And what is the meaning of monotonic function here is that it is means if it is either, means it cannot be both. It is either increasing or it is decreasing. Okay, this is the meaning of monotonic function. Now see from this graph, okay, like see from here to here the function is decreasing. Okay, from here to here the function is decreasing, showing a decrease. Okay, similarly from here to here it is decreasing. Okay, in rest of the cases it is just the blue lines, they are just increasing. Okay, so what does it means? It is having your maximum here, and minimum here and minimum. I hope it is clear. Okay, so definitely what is there, that these points, you can find the points A, B, C, D. Okay, so your A and C are the points of minima, B and D are the points of maxima. But if I say that these points A and C, like C is also minima in its own interval, so C will be called as the local minima. Okay, again A will be called the local minima here. Again B is called the in this interval B is the local maximum, and here it is the local minimum. Okay, may be regarded, like you can see from here, B and D may be regarded as the point of local maximum value. The local maximum value and local minimum value of the function are referred to as local maxima and local minima. Local means in its own closed interval, in its own domain of definition. Okay, so let us understand the value of local maxima minima more precisely. That f is a real valued function and C is its interior point, that C is called as your point of local maxima. When will we C called as the point of local maxima if there exists some h positive such that this f of c is always greater than equal to f of x. See from here, this is the graph. Okay, you see, say I'm talking about this c, I'm talking about this c. You know that derivative here is, first derivative is 0, this is the critical point. So before that the derivative is positive and after that the derivative is negative. Means the curve is moving like this. Okay, so this is the example from positive to negative. So this is means at this point you will always getting a maximum. Okay, and this is called as local maximum. Okay, so what is happening that you see that your point means it is apart from means one step behind and one step ahead. This function is assuming its maximum and minimum values. Okay, so here it is assuming it's your maximum value here, so it is your point of local maximum. Okay, c this is c minus h is towards this side and c plus h is towards this side. Okay, for all x in c minus h n means immediate neighborhood, and this f of c in this case will be called as local maximum value of f. Similarly, c will be called as your point of local minima if for h positive here this f of c is less than equal to f of h, like in this case. At this point means say c minus h is toward this side, c plus h is toward this side, all other values are greater, okay, except this value at this point. Okay, means the curve is like this. Okay, and means here the minimum will be existing. So f of c is here called as, means f of c is less than equal to f of x. That means at c all other values are greater and at c the value is less. Okay, so we say it is the case of local minima and fc is called the local minimum value of the function. Okay, so this is how we interpret this result. Now there is a very important theorem that f is a function defined on open interval I. Suppose c belongs to I be any point, then f has local maximum or minimum at c, then either f dash c is 0 or f is not differentiable at c. Okay, so this theorem says that if a function which is defined in an open interval I, where c say is a point in this interval, okay, then this function will have a local maximum, either local maximum or minimum at this point. Okay, if there is derivative is the first derivative is here, the same concept of Rolle's theorem. Okay, for a moment the rate of change is 0, or that means similarly the meaning of this is also that your function is not differentiable at this. Okay, and the converse of this theorem need not to be true. Why? Because a point at which the derivative vanishes need not to be a point of local maxima. Derivative vanishes means derivative becomes 0, need not to be a point of local maxima or local minima. Now an example is there which nullifies your this theorem. Okay, that why the converse is not true. For example, if I take a function fx equal to x cube, you know it's a cubic polynomial, and its graph instead of being like this, like parabola for your quadratic polynomial, it will be like this parabola will shift towards the downward. Instead of going up like this, it will come from here and start coming down. Okay, so this is the case, it will come down like this. So what happens that f dash x is 3x square, so f dash 0 is 0, but 0 is here neither point of local maxima, you can see from here, nor point of local minimum. Okay, so this point is called as the point of inflection. Okay, where your this is neither point of maxima nor minima. So what is happening at this point means this is not giving you a behavior which will be showing the maximum or minimum character. So this point this is called as point of inflection. A point C in the domain of a function at which either f dash c is 0 or f is not differentiable is called a critical point. You know that critical point is that point at which the derivative vanishes or becomes 0, and f is continuous at c and f dash c is equal to 0. Then there exists a point h greater than 0 such that f is differentiable in the interval c minus h and c plus h. Okay, so this is all clear from the previous definition also. Okay, now what is the first derivative test? For applying this local maxima and local minima, we count for this your first derivative test also. So what is your first derivative test? It is that if f is a function defined on open interval I, then f should be continuous and at a critical point C9 means it should be continuous up to there. Okay. Then if, say, first derivative test says if this f dash x, okay, changes from positive to negative, okay, as x increases through C, right? That means f dash x is positive at every point sufficiently close to the left of C, and this f dash x is less than 0 at every point sufficiently close to the right hand side of C, then C is called as point of local maxima. Okay, now come here. See from here. Point of local maxima. See, the derivative at behind points means like C minus h type of points is positive. Okay, and the derivative towards the C plus h side means it is negative. Means the derivative is moving from positive to negative. So it is a peak which is showing me the maximum. So this is called as point of local maxima. And similarly, if this f dash x changes sign from C from like this, it changes sign from negative to positive. See from here. This negative to positive. Then what is happening here? Here the change is giving you local minimum. Okay. From negative to positive as x increases through C. Okay. F dash C is 0 at every point infinitely close to left of C, and this f dash x is greater than 0 at every point sufficiently close to right of C. Then this is called as point of local minimum. But sometimes it also happens that see from here, point of non-differentiability and point of local minima. See from here, this is also quoting like this. Also, f dash x sometimes does not change any sign. Okay, then in this case C is called as neither point of maxima, local maxima, nor point of local minima, and it is called as point of inflection that we referred in the previous example. Okay, fx is your x cube. And if C is a point of local maxima, then f of C is called the local maximum value of f. And similarly, C is point of local minima, then f of C is called local minimum value of f. Okay. Also, let us see quickly a point where we are discussing the first derivative test. Okay. So an example is there that find all points of local maxima and minima of the function given by fx is x cube minus 3x plus 3. So what will I find? Firstly, I will go for the critical point. So firstly, let us take the derivative and factorize it 3 times x minus 1 into x plus 1. To find critical point, I'll put f dash x equal to 0 and x equal to 1 and minus 1 are the critical point. Okay. Now are the only two critical point which could possibly be the local maxima or minima. Okay. And now firstly I'll take the point as 1. Okay. I'll take as 1. Now what will I check? I'll check the derivative. Now see, come here. Come to this table. Now close to 1 means if it's a number line, it is a 1. Okay, close means towards this side it will be 1.1. Okay, and here towards this side it will be say 0.9. Okay, it's clear. It's a point behind the 0.9. Okay, so see, I'm just checking this f dash x here. So it is 3 times x minus 1 this. So see from here, if I'll put a 1.1 here, what will I get? This is positive, this is positive, this is positive. So it is greater than 0. For 0.9, it will be outside positive, this is negative, this is positive. Overall result is negative. Means it is changing sign from positive to negative. Okay. And for minus 1, I'll take to the left, I'll take the to the right, I'll take point minus 0.9, and to the left I'll take minus 1.1. So when I'll put minus 0.9, I'll find it is this result is negative and this is your positive. So from positive to negative means it is the point of maxima, and from negative to positive means it is the point of local minimum. Okay. Now let us start with second derivative test. Okay. So f is a function defined on interval I, and C is a point inside your interval I. Then f should be twice differentiable. 2 times derivative should be existing. So by the name second derivative test we can apply. Okay. So it should be twice differentiable. Then x is equal to c will be called as point of local minima if this is f dash c is 0 means the critical point we will be obtaining, and at that critical point the value of this double derivative, second derivative, okay, it is less than 0. See, always remember, for local maxima this double derivative at that critical point its value should be negative, okay, for maxima. And for minima this c will be your minima if f dash c equal to 0 means again the critical point and double derivative at that critical point is positive, greater than 0. Okay, so you should always remember that double derivative is less than 0 for local maxima and is positive for local minima, and f of c is called local maximum value here, okay, and fc is called local minimum value here. Okay, so this is local minimum, and this test will fail if your first derivative either becomes 0, okay, or the first derivative giving me critical point but second derivative is 0, okay. So at least you should have a second derivative so that I can apply this test. So let us see a question. Find local maximum and minimum values of the function f given by your fx is equal to your 3x4 plus 4x cube minus 12x square plus 12. So let us start the steps. Firstly, I'll find the first derivative, that is 12x cube plus 12x square minus 24x. Take 12x common and it is 12x into x minus 1 into x plus 2. So next step is to find the critical point. So put f dash x equal to 0, I'll get the critical point as 0, 1 and minus 2. Okay, from here x0, this x1 and x minus 2. Now double derivative. So it is 36x square plus 24x minus 24. Take 12 common. It is 12 times 3x square plus 2x minus 2. Okay. Now I have to check apart from this absolute maxima and minima. In this we will check this second derivative at only critical points 0, 1, minus 2. So evaluate the double derivative. It is minus 24 for 0. At 1 this value is 36, that is positive, and at minus 2 it is 72, which is positive. So what do I conclude? That second derivative test, we say x0 is a point of local maxima. Okay, this, you know, it's a reverse process. The second derivative should be negative, then it is maxima. Okay, and the maximum value, local maximum value, I will obtain by putting this 0 in x here, not in f dash x or double dash, but in f of x. So f of 0 will be here, so you can see clearly from here it is 12. Okay, so your this x equal to 0 is the point of local maxima, and the value is obtained by putting x0 at the fx. Okay, and your this x f of this your 1 at minus 2, it is having the local minimas. Okay, the local minimas, and for your f at x is equal to say minus 1, I will put the value here minus 1, so I'll get the answer as minus 2, and f of 1 when I'll get it as 7. Okay, and f of minus 1 is your 7, and f of minus 2 is coming out to be here as minus 20 respectively. So this is how I will get my respective values of local maxima and minima. Okay, kindly make a correction here that it is x is equal to 1. Okay, x equal to 1, I'll get the value f of 1 is 7. Okay, and your like this from here 1 3 plus 4 is 7, and 12 get cancelled, and f of minus 2 will give me minus 20. Okay, so this is how you will get it. It is just x is equal to 1. Okay, so kindly make it a correction. Please make it a correction that here I will just not take this negative sign from here. Okay, it is just x is equal to 1. Okay, so this is will give me the value as 7. Okay, so local minimas are existing here, right, and maxima is existing here, but the smallest one is this. Okay, so minimum I will say that it is existing at this also and this also, right. Now next theorem is that f is a continuous function on interval I equal to closed interval ab, right, and f has absolute maximum value and f attains it at least once in I. Now this is the question of absolute maximum. Okay, then it will be attaining this absolute maximum at least once in this interval. Okay, it will attain its maximum value. Also, f has absolute minimum value and it will also be attained in the interval. Okay, so that means if a continuous function is there where in an interval I, closed interval AB, then definitely it will at least once it will attain its absolute maximum or minimum value inside this interval. Okay, that is, let f be a differentiable function on closed interval I and your c is any point interior to it. So first thing is f dash c equal to 0 if f attains its absolute maximum value at c. Okay, and also means this is the critical point. We're talking about the critical point. Means if it is, you know, that this kind of curve is there or either this kind of curve is there. So this is f dash c is 0, both the cases. Either then if f dash c is 0, if f attains absolute maximum at c, and this is again f dash c is 0 if it is attaining absolute minimum at c. Okay, so the working rule here is that you will find all the critical points. Okay, so you will find that point at which the derivative is 0. Okay, also you will find all the critical points, then you have to take all the end points also. Okay, and then what you will do you will calculate the value of the function at all these points, at these critical points also and at the end points of the interval also. Now identify the maximum and minimum out of these. Okay, so the maximum value will be the absolute maximum, greatest one. Okay, and the minimum value will be absolute minimum. Okay, the least value. So let us see an example. Find the absolute maximum and minimum values of the function given by this. Fx is your 2x cube minus 15x square plus 36x plus 1 on the interval 1, 5. So this is my function. The first derivative is 6x square minus 30x plus 36, 6 times x minus 3, x minus 2. Okay, so f dash x is 0. That gives me your x as 2 and 3. Now we should evaluate the value of the point. Okay, where to evaluate? At these two critical points, that is at 2, at 3 and also at the end points of this interval. Okay, whom should I evaluate? Not f dash x but fx. Okay, so I'll calculate at x equal to 1, 2, 3 and 5, the critical point and the endpoints. The function here, f of 1 I'll get 24, for f of 2 I'll get 29, f of 3 I'll get 28, f of 5 I'll get 56. Okay, so what will I get? Now see, the greatest value is your 56. Okay, so absolute maximum value of the function is 56 and is occurring at x equal to 5, and the absolute minimum value is 24. Okay, and is occurring at x is equal to 1. Right, so this is how we calculate absolute maximum and minimum. Now let us see this example. This is a very important question and is a very good one also. An Apache helicopter of enemy is flying along the curve given by, this is the equation, y is equal to x square plus 7. A soldier placed at the point 37 wants to shoot down the helicopter when it is nearest to him. Okay, when it is nearest to him means, nearest means the distance is minimum. Okay, distance is minimum. Nearest means you have to find that nearest distance also. Okay, so that means what I need to do is I have not been given this is the equation of the curve. Okay, this is the equation of the curve, but this is not the, I have to show that the distance is minimum and I have to find the distance. So here the function will be not this, but function it will be the distance function. So what will I start with? For each value of x, the helicopter attains a position at the point x and x square plus 7. Means when x is x, then the y values means the coordinate of the point where it is attaining a position. The position graph or curve is x and x square plus 7. Okay, so distance between the helicopter and the soldier. Soldier is at 37 and this is the position of the helicopter. So I'll apply the distance formula like x minus 3 whole square plus x square plus 7 minus 7 whole square. So it is x minus 3 whole square plus x raised to power 4, right? So function is x minus 3 whole square plus x raised to power 4. Okay, this is my distance. Okay, so I can avoid here the square root sign, because I will just check this behavior. As you know, it is inside the square root, so it is always a positive function. So I should not take the negative one. So I can consider it like fx is x minus 3 whole square plus x raised to power 4, because it's a real situation. So second thing is to take the derivative. So derivative is 2 times x minus 3 plus 4x cubed. Take 2 common, okay, and make the factors as it's a cubic polynomial. So it will be like 2 times x minus 1 into 2x square plus 2x plus 3 equal to 0. Okay, so to find the critical point, I'll put f dash x as 0 now, which will give me x as 1 from here, putting 0, and the second equation as 0. Okay, but this equation is not having real roots. You will check that this equation is not having real roots. So there is no endpoint of the interval to be added to, as moreover here there is no endpoint. Don't take it as a interval. It is not the interval. It is just for the distance between the helicopter and the soldier. Okay, so here what will I do is I will only having a one critical point, that is my 1. Okay, the value of the f function at this point is given by your f of 1. We calculate, and the value from here, the function this is the function. By putting x1 here, I'll get it as 5. So the distance between the soldier and the helicopter is your root of this, because the original function is here. So it is the root of, it is your root 5, that is equal to, okay. So note this function, now this value is either the maximum or minimum. So how come I will come to know whether it is my maximum or minimum? Because I need minimum. Okay, I need my minimum. So root 5 is either maximum or minimum. So what will I do is I will start with f of 0 here. So f of 0 will be my 3. Put 0 here. So it is minus 3 square plus 0 here. It is. So the minimum means the minimum value, or the minimum for value 0, it will be coming as 3, which is greater than my root 5. See, in this question there is a different criteria of checking. How will I check the maximum or minimum value? Okay, instead of applying for those other things, I'm just evaluating the function value as I'm searching out for this. So f of this, my value is 3, f of 0 for this root function, which is greater than root 5. Okay, so which means that root 5 is the minimum value. Okay, it is the minimum value of the function. Hence root 5 is there, which is the minimum distance between the soldier and the helicopter. Okay, so this is a very important question, and this question can be asked with the different your equations of the curve and with different points. So you should know how to execute this question. Okay, so I hope whatever is taught to you is clear, and this is just the introduction part of your maxima and minima, in which we discussed about the concept of maxima minima, the local maxima minima, the absolute maxima minima, and first derivative test, second derivative test, and few examples which will help me in solving my exercise based upon maxima and minima. That will take in on our next presentation. Okay, so till now, please do go through it and practice it well, understand the concept, okay, and learn out how to apply the concept for finding out your maxima and minima. Okay, and in next part we will solve the questions problem based upon this maxima and minima. Thank you so much.